Okay, I took a step back here and just want to point out to you my note here. Notice in our first example with the sharp point, where f of x has a sharp point, this happens at x equals 2, f prime of x does not exist, and notice that f prime of x, the red graph, has a jump in it. It has non-removable discontinuity in the derivative graph. Okay, now let's take a look at example B. The function is discontinuous. Here's a function f of x. It is discontinuous. It has a break or a hole or an asymptote. Okay, in this graph, we would say it has a break. There is a jump from 2, 4, where there's a hole, up to 5, and then up to 6, where there's another hole. Okay, we have the graph of a parabola, a point, and the graph of a downward opening parabola. Okay, what would the derivative graph look like? Well, just like in the previous example, our parabola has a linear graph for its slope. There will be an open circle here at 2, 4. So this is the beginning of f prime of x. Now the point, 2, 5, what is its slope? Well, it doesn't, the derivative of a constant is 0, so we'll say that the slope is 0 at 2. And then here we have a downward opening parabola. It almost looks linear at this point. The graph does look a little funny to me, but our slopes are very big negative, okay, and are going to be getting more negative. So I don't know where they begin. I'm just going to put them in here. That it would be a negative linear slope. A negative linear graph for its slope. Okay, so again, notice at f of 2, f of 2, in the derivative graph, there is a jump. Okay, and the slope on the left, which is getting close to 4, is not equal to the slope on the right, which is some negative number. Okay, slope on the left does not equal slope on the right. So therefore there's discontinuity in our derivative graph. Okay, the third kind of differentiability failure is when there is a vertical tangent to a graph. So do you remember the cubic graph? Right, just to y equals x cubed. It looks like you're changing lanes from north to south, right? At the origin, technically there is a 0 slope right there. Slopes are positive here, slopes are positive here, but right at this point, slopes are actually 0. Okay, well, the inverse function, the cube root function, will, instead of having a horizontal tangent, on y equals x cubed, here we have the horizontal tangent. On the cube root graph, we're going to end up having a vertical tangent. Okay? All right. So here we go, taking a look at what the derivative graph would look like. Slopes on the left are positive. They're positive small and getting increasingly bigger until you get to the vertical tangent, where the slopes are actually undefined. There is no slope for a vertical tangent. Then the slopes are really big positive and decreasing. Okay, so your derivative graph might look like, I'll do it in blue. Your derivative graph might look like this function. Okay, so when there is a vertical tangent on your function f of x, what happens on your derivative graph? F prime of x has an asymptote for its discontinuity. Okay. All right, so taking a look at a theorem here, if f is differentiable at point C, then f is continuous at point C. Remember, continuity was a requirement, or is a requirement for differentiability. Continuity is required for differentiability. That's why we did continuity first. Okay, so you have to have a smooth curve, where the limit on the left and the limit on the right are equal, and the function value is also the same as the limit value. You must have continuity for differentiability. Okay, what's a converse? Do you remember a converse? That's when you switch the if and the then sections of the statement. So it would say, if f is continuous at x equals c, then f is differentiable at x equals c. Okay. So the first one says, P implies Q. The second one, the converse, is Q implies P. Okay, now the question is this true or false? So if a function is continuous, is it always differentiable? Okay, what's happening at these 2 points? We have a sharp point, so we do not have continuity. And in our last example, I'll just make this graph continue. Remember, we could have a graph that has a vertical tangent in it. A little harder to draw. So if there's a vertical tangent or a sharp point, the graph is continuous but not differentiable. Okay, so this converse is false. So differentiability implies continuity and implies that your limit exists. Okay. Is the absolute value function differentiable at x equals 0? Absolute value. Whoops, that's not a good y-axis. Let's try that again. A little bit better. Okay, is the absolute value differentiable at x equals 0? No, because the f prime of 0 on the left, I'll use that notation, f prime of 0 on the left is -1, whereas f prime of 0 on the right, so that kind of means the slope as I'm approaching 0 on the right is +1. Okay, I think actually sometimes they write that notation f prime with the negative here. So what is the slope on the left of 0, and what is the slope on the right of 0? In either case, I'll understand what we're talking about by either of these notations. So if you use either one, I'll know. Okay, so we're going to say, nope, there's a sharp point. Now you can't just say there's a sharp point, right? right? You should really talk about the slope on the left and the slope on the right not being the same. Okay, f of x is, x to the 1/3. Well, what's another name for x to the 1/3? The cube root of x. So remember the graph of the cube root of x. I didn't draw it very well. Better to be done with a graphing calculator to see, right? Okay, and at x equals 0, there's a vertical tangent. Okay, and so the slope is undefined. So nope, no, f is not differentiable at x equals 0. Slopes are undefined. Okay, what's this graph? Does it factor in the numerator? X minus 2, x minus 3. Okay, so this is the graph of f of x equals x minus 2 for x not equal to 3. Okay, there happens to be a hole in this graph at 3, 1. Okay, so again, this is just the graph of a line, goes through -2, +1 slope, and at 3, what happens? There's a hole in my graph. All right. Is this function differentiable at x equals 3? Well, there's discontinuity. With hole at 3, 2. So no, f of x is not differentiable at x equals 3. You must have continuity to have differentiability. Okay, last page. Refer to the figure at the right. Complete the following table indicating at which values on the open interval from -6 to 6 the given function f fails to be continuous and or differentiable. Okay, so let's just take a look at the key places. 1, 2, 3, 4. -4, -1. Fix the +2, and I'm going to say something happened at +5. Okay, what do you think's happening at +5? I think there's a vertical tangent. At 2, there's an asymptote. At 1, there's a sharp point. And at 4, there's a jump. So these are all the places of the first 3 are discontinuity. Okay, so x equals -4, x equals -1, x equals 2, and x equals 5. Continuous? No. There's a jump. And we would really say, so let me rephrase. I don't really want to say there's a jump. I mean, that's sort of the layman's term. So I'll say no jump. Why, though? We're going to say the limit as x approaches -4 on the left does not equal the limit as x approaches -4 on the right. Or you could just say limit does not exist. Okay, let's do all the continuities. Yes, continuous at -1. No, asymptote. Okay, so I'm going to just say the limit does not exist. It's infinite, but it doesn't exist. And at 5, yes, we're continuous. Okay, I'm going to run out of time. And so we'll stop. Why don't you finish and we'll go over it later. Bye.